In this video, we'll examine the forces acting on an object placed on a surface. Initially, we'll focus on a flat surface to comprehend the types of forces influencing an object. Then, we'll transition to an inclined plane to observe how the direction of these forces alters with changes in the angle of inclination. The diagram depicts a block of mass m, placed on a table. It is essential to differentiate between mass and weight, as they represent distinct measurements. Mass signifies the quantity of matter present within an object, and stays consistent. In contrast, weight signifies the gravitational force exerted on an object, and can fluctuate based on the local gravitational field strength. Mass is a scalar quantity, while weight is a vector quantity, always directed in the gravitational force's direction. If we use g to represent gravitational acceleration, weight can be computed as m times g, where m represents the object's mass. Normal force is a type of contact force that arises when two surfaces make direct contact with each other. In such instances, these surfaces can exert a normal force on each other, and this force is always oriented perpendicular to the contacting surfaces. When surfaces are not in contact, they lack the capacity to exert a normal force on each other, and in those cases, the normal force is considered to be zero. In this demonstration, it is represented as n. However, in this scenario, our focus is solely on the forces exerted on the object, and we do not take into account the forces applied to the surface of the plane. When we analyze the forces acting on an object, we refer to the object's free body diagram. Therefore, there's no need to depict the normal force applied to the plane surface by the object. The applied force is a force exerted on an object, either by a person or another external object. In this specific illustration, it is denoted as F of A, indicating the force applied to the object from an external source. Frictional force occurs when two surfaces come into contact and begin sliding against each other. The strength of these forces is primarily influenced by the texture of the surfaces involved and the amount of pressure pressing them together. I will delve into a more detailed discussion of frictional force later in this video. Next, we'll examine how the directions of these forces shift when the angle of inclination is altered. This diagram illustrates the changes in the direction of these forces as the angle changes. As evident in the diagram, the weight always points in the direction of gravity. However, the normal force and friction force adjust as the angle changes. The applied force can vary in direction, but for this example, we'll consider it as shown in the diagram. When you're dealing with vectors pointing in different directions, figuring out the resulting force can get tricky. To make things simpler, we break these forces down into directions that are at right angles to each other. Picking the right direction is key, and it depends on the specifics of the problem you're working on. In this situation, it seems like a good idea to have one direction lined up with the acceleration, and the other one going perpendicular to it. This is because, when applying Newton's second law, it's essential to concentrate solely on the acceleration in one of these directions, while assuming that the acceleration in the perpendicular direction is negligible or zero. In this situation, the only vector that needs to be decomposed is the weight vector. The resulting decomposed vectors are displayed on the screen. These two vectors form a right angle at this point, with the angle being the same as the angle of inclination. The adjacent vector is represented as mg cos theta. The opposite vector is represented as mg sin theta. With all vectors originating perpendicularly, it becomes feasible to add or subtract these vectors in their respective directions. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. Alright, let's dive into a problem to put the ideas we've covered in this video into practice. Picture a mass m placed on a surface, inclined at an angle theta to the horizontal. This object is pulled by a force labeled F of A. Our objective here is to calculate both the acceleration and the normal force. For this specific example, we'll work under the assumption that there is no friction. Additionally, we'll consider that the object is moving in the direction depicted in the animation. The acceleration of the object, moving along the inclined plane, aligns with the direction displayed on the screen. As we discussed earlier, our first step is to break down the weight vector into two components, one along the inclined surface and the other perpendicular to it. This simplifies the process of vector addition in the same direction. You can represent the weight component along the plane's surface as the sign of the angle of inclination, while the component opposing the normal force can be obtained using the cosine of the angle. It is recommended to remember the decomposed weight components for easier problem solving in similar situations in the future. Our next task involves the application of Newton's second law in these two directions to determine both the acceleration and the normal force. Subsequently, we will use the second equation to compute the normal force. It's important to note that the acceleration in this direction is 0. Now that we understand how to calculate the acceleration and the normal force, let's proceed to the next exercise, where we'll substitute the force F of A with a weight. We'll follow the same steps as in the previous example to calculate the acceleration and the normal force. We will refer to the weight on the sliding surface as M1, and the weight affixed to the opposite end of the string as M2. This demonstration shows how the two weights move. Let's sketch the free body diagram of the two objects. Similar to the previous case, we will assume that there is no friction between the inclined slope and the weight on the inclined surface. We will also consider the weights of the pulley and the string to be negligible, and the string does not stretch when the two weights are attached to it. Additionally, we assume there is no friction between the pulley and the string. Due to these assumptions, we can consider the tension of the string on either side of the pulley to be the same. However, if we account for the weight of the pulley, the tension in the string on either side of the pulley will not be the same, due to the inertia of the pulley acting on the string. Alright. Our next move is to put Newton's second law into action for the two weights, so that we can figure out the acceleration and the tension in the rope. If we assume the acceleration of weight M2 to be A, in the downward direction, then the magnitude of the acceleration of weight M1 has to be the same, but along the plane surface. But before we jump into Newton's second law, we need to break down the M1 weight into two parts, one following the acceleration's direction, and the other going perpendicular to it. We're basically splitting up all the forces in our setup into two parts, each at right angles to the other. This ensures that the vector sum gives us the net force acting along and tangential to the acceleration. Doing this makes our job easier, because we're focusing on just one component in the acceleration direction. Please remember, this step is essential, and should be done after sketching the free body diagram, and before diving into Newton's second law, whether for the whole system, or individual objects. We have two methods available to us to calculate the acceleration of the two objects. The first approach involves independently applying Newton's second law to each object to calculate both the acceleration and the tension in the rope. Alternatively, we can treat both objects as a unified system, ignoring the internal tension, and apply Newton's second law in the direction of acceleration. I will demonstrate both methods and prove that the results remain consistent, regardless of the approach chosen. Let's start by considering these objects independently, and then apply Newton's second law. For weight M1, we will apply Newton's second law along the inclined surface in the direction of acceleration, and derive this equation. Next, we will apply Newton's second law to the weight M2 in the downward direction, and derive the second equation. Now, we can add the two equations to derive an expression for the acceleration. We can use this calculated acceleration value to determine the tension by substituting it into either of the two equations mentioned earlier. This will yield an expression for tension, as demonstrated here. We do not necessarily have to follow this approach. Instead, we could consider the two weights and the string as a single unit and apply Newton's second law to the whole system, in the direction of the acceleration. In this approach, we will not consider the tension in the string since it gets cancelled when we consider the whole system. The external forces acting on the system, along the direction of acceleration, are m1g sine theta, and m2g. While these two forces are not aligned in the same direction, we take into account the direction of acceleration, which is common to both weights, and apply Newton's second law, as indicated here. An important aspect to remember, when applying Newton's second law to a composite system, is to identify the direction of acceleration that is common to all the objects, and then apply Newton's second law in that direction. This involves summing up all the forces in the direction of acceleration, and subtracting the forces in the opposite direction, to determine the net force acting in the direction of acceleration. Additionally, you consider the collective mass of all the objects experiencing the acceleration. This provides you with the total weight of the system. You will become more familiar with this concept as we work through more problems in upcoming videos, particularly when we tackle pulley-related problems. It's important to note that both methods yield the same solution for the acceleration. Finally, we will apply Newton's second law in the direction of the normal force. The acceleration in this direction is zero, as the object does not move in this direction. Consequently, we obtain this expression for the normal force, as shown here. I hope the concepts discussed in this section were clear. In the next video, we will explore how friction influences the movement of an object on an inclined surface. Thank you for watching this video until the end. I hope you found it informative and helpful. If you haven't already, please consider subscribing to the channel. Until we meet again with another video, take care and goodbye.